Swayam Prabha. Digital India. Educated India.
Good morning to everyone present here. It is my honor and privilege to introduce Professor T.P. Radhakrishnan, an emeritus professor at the University of Hyderabad. As an highly esteemed chemist, his research in molecular functional materials and nanocomposite thin films has had a significant impact in material sciences. In recognition of his distinguished contributions, he has been awarded the prestigious DAE Raja Ramana Chair, one of India's highest scientific honors. With decades of dedication to research and mentorship, he has shaped generations of scientists. We are honored to have him with us today. Please join me in welcoming Professor Radhakrishnan.
Thank you, Rishi. So I'll get started. So all my details are here. So I suggest that you note down especially the email so that we can continue to converse even after you people leave, I leave from here. Okay, if you have any questions, comments, suggestions, ideas, it's always good to interact. So age-wise, we are very far apart, but I think in terms of intellectual curiosity, liking for studies and so on, I think we are all similar. Okay. So there is something sitting here. Yeah. So this is my address and some details are here. And this website will give details of what kinds of research we do in the university at Hyderabad. If anybody is interested further in that direction, you are welcome to contact me. So today I'll talk about this idea called molecular materials. I don't know if you have been exposed to this term, molecular materials. If I say just materials, can you tell me what comes to your mind? There are various kinds of materials, right? Anything, huh? Wood, steel, perfect. Anything else? All around us, huh? Plastics, yes. These are all materials. Polymers, yes. Plastics, polymers. Ceramics, cement, glass. So everything all around us, I mean, we are sort of sustained. Of course, we ourselves are a conglomeration of various kinds of materials, right? Starting with the small molecules, biomolecules, bones, brain. Everything is composed of some material. Of course, for life, you need to go beyond materials, no doubt. You had a great talk on biology and game theory earlier, right? Which was probably more of mathematics and connecting to life sciences. So I will work at a much simpler level, mostly chemistry because I'm a chemist. So materials is again a discipline where chemistry, physics, biology, everything has to come together. So as a chemist, we try to make them, study them, and so on. Physicists also try to understand properties. So we need to learn a little bit of physics to understand materials. And some of the applications would be in biomaterials and so on. So there will be a lot of biology, medical applications, all kinds of things. So this field called molecular materials, because the idea of molecules is very, very important in chemistry. If I were to ask somebody, what is the unifying idea in chemistry? I think chemistry as a subject is taught at the high school level, right? So Rasayan Shastra. So if there are all kinds of chemistry, right? If you have heard about organic chemistry, inorganic chemistry, physical chemistry, theoretical chemistry, analytical chemistry, and so on and so forth, or the medicinal chemistry. So what is a single concept which comes across all disciplines of chemistry? Atoms, molecules. I would say molecules even, because with single atoms, you can do practically all chemistry handles molecules at some level. Of course, they are built from atoms, but once you have some bonding between atoms, maybe covalent type, electrostatic type, various kinds of interactions, you make molecules. So atoms, of course, physics also handles atomic physics quite a lot. So the single unifying concept to my mind, this is of course my personal opinion, is the idea of molecules is very central to chemistry, any kind of chemistry that you talk about. So materials built up of molecules is a sort of a domain where there is a lot of interest, a lot of basic physics comes into understanding them, and a lot of applications and so on. So this is the broad area that I will talk about, and how it emerged more than a century ago, and how it evolved in the last 40, 50 years, and sort of perspective of where things are moving. And as you said, steel and wood and so on, there are a lot of materials, but this is sort of a fairly unique class, having its own identity. So what I will do is I'll start with some history, because history is important for all of us, how you grew up from your lower KG class and so on. That history is important, how you built, how you reached 11th class. So if you look at this term, Story of Civilization, is a very famous title of a book by somebody called Will Durant and Ariel Durant, a very famous book in philosophy, Story of Philosophy and so on. But I borrowed that name, so I have to give courtesy to that. But I'm putting these pictures here. You must have studied history at some point. So you talk about the growth of civilization, human civilization. Start with the Neanderthals and so on. Stone Age, where they did not have metals. This is roughly the time frame in history books. Copper Age, it's called Copper Age. Stone Age, Bronze Age, when alloys started coming. Iron Age came much later, more difficult to mine and purify and so on. And now, of course, we continue to talk about this. So now people talk about our current era as Silicon Age sometimes. Why? Semiconductors are primarily based on silicon. A lot of industries, so all our electronic devices are based somewhere along the way on silicon technology. So sometimes people call it the Silicon Age. And there is a lot of speculation that things are moving towards what sometimes people call a Carbon Age, where carbon nanotubes, fullerenes, all these may become very important in the technology. But this whole picture I put up, in fact, I made it in a particular way because stone is basically silica and silicates. So there is silicon there, and wood is mostly carbon. So there's some interesting sort of rhythm in the evolution of civilization. So we have come back to carbon in a very different form, of course, to the Neanderthals and Stone Age and silicon and so on. So the important message here is that this whole thing tells us that the evolution of human civilization was defined using the type of materials people used. As you said, steel and cement and so on today. So at one time it was stone, at later copper came. So everything is defined, even our human civilization, how it progressed, is sort of described using material. So materials sort of define our existence. So that is why it is important to learn about it, to understand, as a chemist, to make new materials, as physicists, to understand them, and so on and so forth. So if you now go a little deeper into technical things, materials obviously come in many forms. Just to drink your orange juice or tea or coffee or whatever, you have many ways. You can have steel, which is basically a metal or alloy, and you have ceramics, somebody mentioned ceramics, polymers. So the same function, I mean, slightly different situations. Of course, this is very light, this may be a little heavier, this may break. So there may be different physical properties, but they all serve different functions. So there are different kinds of materials which we use day to day for slightly different use applications and so on, cost, recyclability, all kinds of issues. Now, of course, plastics have come into a lot of question because of sustainability of the nature and so on. And there are, of course, very many. Food you mentioned is a composite. It has all kinds of things fixed together. Depending on the nature of the wood, the compositions may vary. Semiconductors are, of course, the heart of the electronic industry, biomaterials, and I want to introduce the idea of molecular materials, which is some commonality with many of these things, as we will progressively see, but they also have a sort of unique defining feature. So the way to think about it is, if you look at materials as a whole, like the examples that you mentioned, steel and ceramics and so on, many of them are started with some precursor. Precursor means something starting material, and you take it through various routes. It could be ceramic routes, what are generally called, where you use high temperature, high pressure and so on, and you develop a material. Or of late, there has been what are called soft chemical methods, where you use solution chemistry. You use some solvents, relatively low temperatures, normal pressures and so on. So as an example is this, that as you mentioned, glass, for example, is a very important material. And we know it comes from sand, silica basically, chemically speaking. And you have to take it through some high temperature, you have to melt it and then quench. So they form what is called a glassy state, which does not have a crystalline arrangement, but the silicon oxygen bonds also form networks, and sort of thermodynamically speaking, sort of what is called a metastable state. But this is basically how you go from a precursor to a material through some process. Now, molecular materials have a way of defining, or at least the way I think about it, is you can define it with a slightly different way, where you start from a precursor, you go through a well-defined intermediate state, we call it molecules, and then go to the material. Now, what does that mean? As an example, there is a term that chemists use called synthesis. Organic chemists make mostly carbon-based compounds. Inorganic chemists may make metals and oxygen and various other elements may come in. So, but essentially there is something called synthesis. And the molecules are then assembled. So there is a subtle difference between these two steps. So one is usually what we call a covalent bond formation. There have been very strong interactions between atoms. You tie them together as a schematic picture. And when you say assembly, it is primarily based on much weaker interactions. So covalent forces are much, much stronger, much more difficult to break. Hundreds of kilocalories per mole is the energy involved. And these things called non-covalent interactions, and there are very many. It could be, for example, hydrogen bonding is a term you must have heard, right? In water and so on, it's very important interaction. So these are much relatively speaking, much weaker. Dispersion forces, where you have inducing a dipole moment and so on, there will be some weak interactions, much lower energies compared to covalent forces. So those are these weak, so-called weak interactions or non-covalent interactions. So the assembly is controlled by that. Now, this may be weak, but extremely useful, very versatile. One of the utilities is that you can easily take them apart. You can go back from the material. Going back from glass to sand is a little trickier. But going back from a material, I'll give you many examples as we go along, a molecular material to go back to the molecule, because the interactions are much weaker, very easy to take them apart. Then you can ask the question, why do you want to take them apart? Suppose you have made a molecule, as a chemist you made something, assembled it using some interactions, and finally the material by definition has to serve some function. Either some utility, some steel, for example, you can build something with that, or some other material, plastic, you may make a cup, for example. So it has to serve some function. So that is how you define a material. Otherwise, it's simply a solid or a gel or whatever. But once it serves a particular function, we call it a material. So if that material property is not exactly what you wanted, then you can just take it apart because the forces are very weak. Then modify the molecule using some further synthesis and again assemble them back. So you can go back and forth so that you can finally optimize it's sort of a cyclic route. You make a molecule, build a material, not happy with it, it doesn't serve the purpose that you wanted it to, then you can break it apart, redesign. You can do this cyclically until you reach what you really wanted. So this is of course the heart of material synthesis, assembly and so on. So that is the beauty of it. Now this is just sort of, again, I'm very fond of history. So this history is sort of brief history. You've heard of A Brief History of Time? You heard this famous book? Yeah, Hawking's, yeah. So this is a brief history of molecular materials, okay? It's sort of my list. There are many other things one can put, but I'll go through each one a little quickly just to have a feel of what it means. Liquid crystals is one of the very oldest. There might have been a few more things, but a very well-defined thing. And it dates back to 19th century, long time back. But you have heard of LCDs, right? Liquid crystal displays. They're all based on this. In fact, there was a Nobel Prize awarded for liquid crystal display technology and so on several years back. So that liquid crystals are mostly made up of organic molecules, simple molecules which are very weakly bound together. So you can take them apart, you can modify them. So a lot of interesting things you can do with them, which you cannot do with something like glass, which is very robust. So that is where the versatility, and it is extensively used in commercial application. But that stayed like that for more than half a century, or almost a century. But in the 50s, that is again many years back, several decades back, there was a very important discovery where perylene is an organic molecule. I'll show you later on. Till then, most of the organic molecules or organic materials, like plastics that you see, they are all electrically insulating. Like in fact, many of the switches you make using insulating materials, bakelite or plastics and so on. So that is because you want insulators. But if you want a conductor, very few organic materials can be used. So in the 50s, somebody found that you can make organic materials which are electrically conducting. In fact, people used to start calling them synthetic metals. That means you're actually synthesizing. Earlier metals are good conductors. What are the good good electronic conductors or electrical conductors? Copper, silver, gold, platinum, all these are all metals or metal alloys or some metal oxides, sulfides. There are several conducting materials, but they're all based on metals in some way. But this was the first time in the 50s, a very important paper came out. We showed an organic molecule, you can make it electrically conducting. So that itself was very fascinating. So that triggered a lot of activity and a lot of other things came. So we will go through this list one by one a little quickly just to have a feel of what these molecules are, what these materials are, and then we'll go a little deeper. So into the chemistry and so on. So liquid crystals, this is sort of cartoon picture of it. There are various forms. So what is interesting is the important term here is a partial ordering. See, the idea of ordering itself is a very complex idea. For example, if you take a crystal, you have heard of crystals, right? Crystals are perfectly organized array of atoms or molecules. So if I have a molecule, for example, these tiles here, this is actually a crystalline arrangement. You have some squares which are repeating along each direction. This is a two-dimensional, but I could make a three-dimensional crystal, building more of these bricks on top. So you can have an ordered structure, perfectly ordered. You can have a completely disordered structure, for example, in a liquid state, water. Water has H2O molecules, right? They are hydrogen bonded to each other, but there is no repeating order. They are all each water is connected to several molecules. They are further connected, they form a network, but no what is called a periodic order, like you are all sitting in a periodically ordered state. So in crystalline forms, it is always like that. There are of course defects where something is missing, but crystalline order is still a reproducible sort of ordering. But in water, for example, it is the other extreme where there is absolutely no order. But then the term liquid crystal itself is very evocative. It tells you there is some liquid property, kind of like some crystal property. So these are things which are called partially ordered. Look at this picture. If I ask you, are they ordered? It's a tricky question. I can say they are not ordered like a crystal, but you can see they are all sort of elongated ellipsoidal molecules, but they are all orienting in that direction roughly. There is something usually called a director axis. So along that axis, there is a small distribution of angles. So some theta angle, if you take, there will be a distribution of theta in the range some 5 to 10 or 15 degrees. But all of these things are ordered roughly. So that is a partial ordering. Now this is very important. And you can have that ordering forming a sort of helical ordering, which is called a chiral nematic or a cholesteric phase. Cholesterol, you have heard of cholesterol, no? So basically this was actually the original discovery in 1888 as an ester of cholesterol called cholesterol benzoate was the first molecule to be discovered which forms this thing. Now how did he know that there was some peculiar state? Normally if you take a solid and try to melt it, solid will be immobile. Once you make it go through the melting temperature or melting point, it becomes a liquid, very clear. It's a phase transition from solid to liquid. Liquid crystals have something in between. So they become a little fluid, but they don't flow easily. I mean, they have a little flowing property, but they are not like liquids. They will fill space, but they are not completely disordered like a liquid phase. So something in between. So they usually have two melting points. You take the solid crystalline form, it becomes something like in between there will be some partial ordering which you can detect by optical microscopy and so on. That means there is some ordering of molecules. How do you know that? You use polarized light. If you use polarized light, if there is no order at all, in any direction they will absorb equally. But if there is some partial ordering, they will absorb a little more in one direction than the other. So you have some ordering. That means under a microscope you can observe it using polarized light. But then if you go on heating it further at some second temperature, they'll become completely fluid. There is no ordering at all. They have two melting points. These are called thermotropic liquid crystals. There are slightly different liquid crystals also, but those are detailed. So this was a very important discovery, and various kinds. Here again you can see there's a slightly more ordering. They have this directional ordering and there is some layer structure. So they have different names, pneumatic, smectic and so on. But what is important is these things form the basis of many of these display systems. They have various applications, but display is one of them. The trick involved how to make displays out of them, I will come to toward the end of the talk when we go a little deeper into the physics of this. We will mention this towards later at some later stage. Right now I just want to tell you what are the materials. This has to do with the fact that you can apply electric field, magnetic field and so on and make these molecules, because they are so weakly interacting, you can twist them and turn them. In a crystal, very difficult to make the atoms and molecules move. But here the interactions are so weak, apply a weak electric field and you can orient them. So you can do tricks with that. That is how these displays are created. We'll come to the details later. And some actual molecules, these are only cartoons. Some molecules like this, these have two benzene rings, some polar structure and so on and so forth. So all kinds of molecules are known to form this liquid crystalline state. And close to home, in Bangalore, there was a very famous physics professor called Chandrasekhar, not the other astrophysics S. Chandrasekhar. This is another S. Chandrasekhar, who discovered so-called pneumatic discotic liquid crystals. Again, these are disc-like molecules. The other earlier ones are sort of rod-like molecules. So this is called discotic liquid crystals, and molecules like this, a lot of benzene rings and so on, fuse together. So they form again partially ordered structures. You can see these pictures. You can again see some ordering, but not absolutely crystalline order. So there are a lot of interesting examples. So this is one of the early molecules. You can see these are all molecules, right? Organic molecules with covalent bonds, maybe some coordinate covalent bonds, but they are strongly bonded systems. And between the molecules, you have weak interactions like hydrogen bonds and so on. So this is the sort of defining picture of molecular materials. Now we continue. So as I said, in the 50s and the 60s, so 60s in the time when I started growing up, like you guys, so you can imagine, last century. Yeah. So there was beginning of the so-called semiconductors based on organic materials or organic molecules. So what is this molecule? So well-known semiconductors, as we have already mentioned, silicon, gallium arsenide, gallium indium arsenide, a lot of inorganic semiconductors are known. But so this is the well-known ones. But this discovery in 1954 by a group from Japan showed that this is clearly a simple organic molecule. It's a hydrocarbon, aromatic hydrocarbon. It's all carbon atoms with some hydrogens sticking out. So if you treat it with a little bit of bromine, and bromine is like a halogen, right? It's one of the halogens. So they are all electron affinic molecules. They can pull out electrons. So this fellow has a lot of delocalized pi electrons. You might have heard of pi and sigma bonds. So ethylene molecule has a sigma and a pi bond between carbons, right? So this has a lot of pi electrons. So those electrons are floating around and they are relatively easy to pull out compared to sigma electrons. So the bromine can oxidize them partially. So you get some things like this. You can see BRX. So the X may be 0.1, 0.2, not exactly stoichiometric. These are called non-stoichiometric compounds. And this apparently showed very interesting property. The resistivity is 8 ohm centimeter. So that is not a very high conductivity, but it is extraordinarily high compared to organic molecules. I'll show you some charts of conductivity later on, like Teflon and plastics and so on. They are highly insulating. Their conductivity will be 10 to the power minus 10, minus 12, minus 15 ohm centimeter. So they are extremely weakly conducting. And there is something about magnetic susceptibility, which is also important because these electrons are moving around. If you have, they have something called a diamagnetic susceptibility, but it was unexpectedly very different from what was expected. So expected value is this, and they have much higher, much lower diamagnetic susceptibility. So these are some details, but later on, people showed that a molecule like this is basically, I don't know if you've heard of a molecule called quinone. It's a benzene ring with the two oxygens connected with a lot of double bonds and so on. So if you replace the oxygen with these groups, the importance of cyano groups is that it can pull electrons very easily. They are, electron withdrawing groups. So this whole molecule has a pi system which can pick up electrons very easily. Like two extremes, like those which are very electropositive, very easy to ionize. What are those elements? In the periodic table, if you look, the alkali metals, right, in the left side, the sodium, potassium, lithium, and they are very easy to remove electrons. Their ionization energy is very low, 4 to 5 electron volts, or even less, 3 to 4 electron volts. That is the type of energy. The halogens on the other end are good electron acceptors. They have high electron affinity. So these two terms, ionization potential and electron affinity, tells you how easy it is to remove electrons or add electrons. Now, organic molecules are also there. For example, this fellow can easily take electrons. So they have very high electron affinity, about 3 to 4 electron volts and so on. So that means they can easily take electrons from somebody who is willing to give. And who is willing to give? Alkali metals. So if I take a sodium atom and mix it with this, the sodium will transfer an electron. So this will become an electron will be added. It forms an anion radical. So once they become anion radicals, they have various magnetic properties, optical properties, and so on. You can get highly colored systems and so on and so forth. So here also, because they are able to lose electrons easily, these aromatic condensed organics can lose electrons easily. They have relatively low ionization potential. So there are a lot of molecules prepared like that. Sorry, yeah. 1 second, yeah. So using these organic molecules, people started making various kinds of semiconductors because now you have changed the electronic structure. You have some unpaired electrons, free electrons. So if you pack these molecules, these electrons can move along the stacks and conduct electricity. Those details of technical things we will come to a little later. So this was an important discovery. Then there is something called nonlinear optics. Again, very briefly, I'll introduce you to this. These are terms which are important in optics. So again, organic amino acids, you might have heard of amino acids, very important in biology, right? So amino acids are also, many of them are chiral. That means they have an optical activity. They have some carbon atom which has some asymmetric distribution of molecules or atoms connected to them. So you could people have made what are called nonlinear optical materials. Just to give you an idea, a simple example, urea is a very well-known molecule. It's used in fertilizers, for example, right? And in biological systems also, uric acid and so on. These are very important biologically. So urea has a very interesting structure. So these dotted lines, what are those? Those are the hydrogen bonds, right? And these are the so-called weak interactions. So this is the classic example of a molecular material. So I have a molecule which is very strongly bound, nitrogen, hydrogen, carbon, oxygen, and so on. So they form a very strongly bonded system. But between them, there's plenty of hydrogen bonds. Now, it is not just blindly they have hydrogen bonded them. If you can look at the structure, if you know what is stereochemistry, when you draw things, if you can follow that, this row of molecules are actually perpendicular to the plane. These two are in the plane. Now, this is very important. Because of this, the whole overall organization of molecules does not have some symmetries. For example, there is no inversion symmetry. These are things which you will learn later on. There is symmetry. For example, this square has 4-fold rotation symmetry. If I rotate it by 90 degrees, it looks exactly the same. If I rotate it by 180 degrees, it looks exactly the same. 270, it looks exactly the same. So that is a symmetry. But if I take a pentagon, I have a different 5-fold symmetry. So these are called symmetry operations. Now, things which are, for example, if you take water molecule, if I imagine an axis through the oxygen atom, if I rotate the hydrogens, it will look exactly the same. So this has a 2-fold rotation symmetry. You can put a plane, mirror plane at oxygen. So 2 hydrogen atoms, if you can reflect, They again look the same. So these are called symmetry operations. So this is very important in chemistry to understand electronic structure and so on. So the point here is that this organization of urea, because of all these hydrogen bonds, the crystal will not have a center of inversion. Center of inversion means if you have as an example, I'll take a cube. Imagine a cube. So at the center, that point is called a center of inversion. Why? Because if I take any vertex, you have to imagine the cube in your mind. If I take this vertex, if I reflect it through this point, it will go to the other corner. So all the points, so if you do that operation on the whole crystal, the cube, it will look identical. Suppose I gave you a cube, I asked you to close your eyes and I moved all these points through the center, then you opened your eyes, you will not see that I have done any operation. So this is called a symmetry process, symmetry operation. But if I take a tetrahedron, will I be able to do that? If I imagine the center again, if I do, it will look like it has got inverted. Then you will say, no, 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 you did something, it is not looking the same. So that's not a symmetry operation. So it does not have a center of inversion. A cube has. So similarly, this crystal, now why this is important, if you go through a little bit of the physics of this nonlinear optics, then you will see if you don't have the center of inversion, then, and also there are some properties of polarizability and so on, then you can use these crystals to change the wavelength of lasers when you send it through them. So this is one of the areas of nonlinear optics. We don't have time to go into the details, but crystals like this, again with chirality, again they cannot form centrosymmetric crystals. They are crystals, if I organize, this is called a prolinol derivative with a nitro group. So there is a donor group, acceptor group and so on. Amino groups are electron donating. Nitro groups are electron withdrawing. So you can create a dipole along this, and these molecules can be organized in a crystal. Because of the chirality, they will not have center of inversion. And whenever you don't have center of inversion, you can produce some nonlinear optical effects. We will leave it at that moment. If anybody is interested, I can explain why. You have to write a few mathematical equations and you can prove this very easily. So, but the point is they can be used in what is called second harmonic generation. To put it very simply in terms of application, you have heard of lasers. Lasers are very important, even surgery. Now, a lot of surgery, eye surgery, for example, you can do with lasers because they are very coherent radiations. They are monochromatic, they are coherent, and they are very intense. Coherent means all the waves will travel in phase. So you can have very high electric fields from them. These are very important. Now, the wavelength of these lasers are also important because for a certain particular purpose, you may need a green laser. For something else, you may need a red laser. So how do you change the wavelength of the lasers? One is to buy a new laser with a different, what is called a cavity, but it's a very expensive thing. Using nonlinear optics, you can send a wave of laser through a crystal and it will change the wavelength through this nonlinear optical process. So you can take an infrared light and create a visible light, things like that. So there is some physics behind it. So these kinds of materials can be used to do that. Again, classical, many of the lasers that you buy commercially, many of them are based on various inorganic materials like neodymium. There is a carbon dioxide laser, there is dye lasers. There are a lot of lasers, mostly based on inorganic materials and so on, which are very sturdy, very important. But in principle, many of these organic molecules can also be used. So, okay, this is just a brief introduction to this. I will not go through all the details. This depends on this coefficient. So you can do doubling of frequency, mixing, and so on and so forth. So there are various applications of this. For example, this electro-optic effect in our day-to-day life, it is used in all the fiber optic communications. You know, now many of the signals, earlier days, everything went through copper wires, through electrical signals. Now a lot of them go through light signals. Optical fibers basically send information using optical waves. Now, how do you convert a sound, for example, what you talk on a phone, into an optical signal? So you have to convert the sound into electrical sort of signals and the electrical signal to optical signal. That is called electro-optic effect. All that comes from these nonlinear effects. So that optical thing goes through these fiber optic communication lines and then get converted back. That is how the telephone conversation, for example, goes through an optical fiber. So those things need these nonlinear optical materials. So this is just an example, infrared laser. Infrared, of course, is not visible to the eye. I just put a red line here. You can convert it into exactly half the wavelength or double the frequency. So these are all done using nonlinear optics. So just the point I wanted to make is that using organic molecules, you can do such things. compared to inorganic material or the non-molecular materials. Continuing, metals. Of course, this is much more, I'm just going sort of chronologically, okay, just to tell you that's what I said, the evolution of materials. So again, in 70s, see, these were all semiconductors. So once these organic molecular materials were discovered which could show semiconducting property, you know the difference between metals and semiconductors? How do you distinguish them? This is basically a physical property. Metal doesn't mean metal. It could be any material which shows metallic conductivity. So what is the basic way of distinguishing? Have you studied? Huh? No, not quite. See, the electrical conductivity will go down because there will be a lot of lattice vibrations and so on. No, see, the distinction comes from the temperature effect. Because semiconductors are relatively lower conductivity compared to metallic conductors, but that is only a relative. There are some very good semiconductors with high conductivity, very poor metals with low conductivity, but the temperature dependence is the critical factor. For metals, if you heat, the electrical conductivity will go down because there will be a lot of lattice vibrations and so on. Semiconductors have something called a band gap and so on. So when you heat, you create more mobile electrons or holes, conductivity goes up. So this is the basic distinction. So semiconductors, increasing temperature normally increases the conductivity, metals decrease. So this is sort of broad general definition. So people wanted to make organic materials which are electrically conducting, like a metal. So there was a lot of interest in that, and I'll show you a few of these. And there are things called, polymers. As we said, by and large, 90% of the polymers are non-conducting, completely insulating, perfect insulators and so on. But then people discovered polymers which show electrical conductivity. So again, these are molecular systems. And there is something called superconductors. You must have heard this term also. Now many of the MRI machines in the hospitals, they need very high magnetic fields. So they use superconducting coils. Superconductors they conduct electricity with zero resistance or infinite conductivity. So that they have again very, very exotic materials. You need very low temperatures and so on. So many of the classic example is mercury. The first discovery came in 1910 or something like that, more than a century ago, where somebody showed that mercury, if you cool, mercury is a metal, you know that, in normal conducting temperature. It is metallic conductivity. So, but if you cool it, as I said, the metals usually, the conductivity will go on increasing or resistivity will keep on decreasing. But somebody, a very famous name called Kamerlingh Onnes, he discovered in 1910 or 1909 or something like that, that at some temperature around 4 Kelvin, very close to absolute zero, the resistivity completely vanishes, zero. Then he called it the superconductor. And there's a lot of theory and a lot of physics behind it. But so mercury, tin, lead, various alloys, niobium, germanium, various alloys are known which are superconducting. Many metal oxides, but mostly materials which are based on atoms and anions and cations and so on. But then people found that organic molecules can also be made into superconductors. So just to show you a couple of pictures, so well-known metals are this. So this is a molecule, this I showed you earlier already. These all have long names, okay? I'm not bothering you with the names. So this has some, again, organic molecule with some sulfur atoms. If you combine the two, they show metallic conductivity. So that people started using the term synthetic metals. See, you cannot synthesize gold or you cannot synthesize silver. You have to mine them. And from their ores, you extract them, you get metals. But these are organic synthesis in a chemistry lab, in a conical flask or whatever, in a reflection flask or distillation and so on. You do regular synthesis and you can make these compounds. So they are called synthetic metals. And this complex, so this is a good electron donor, this is a good acceptor. You bring them together, the electron jumps from one to the other, and then you have stacks of these molecules. I don't know if I have a picture, maybe somewhere. Yeah, things like this. You have molecules which are packed like our dosa or chapati stacks. So these are planar molecules. So they stack, and once you have two stacks of donor and acceptor, few electrons will jump from the donor stack to the acceptor stack. So you have some partial charges on these. So this is called partial ionicity. I'll show some descriptions later on. So they can conduct electricity. Now, very interestingly, they have crystal structures, right? These are crystalline materials. So if you measure conductivity, if you make a crystal, let's say this is a crystal of this compound, the molecules are stacked in this direction. If you measure conductivity in this direction, it will be very high. If you measure in this direction, it will be very low. So these are called anisotropic conductors. So these are all things which are very unique. In gold, for example, you will have very little anisotropy because they have certain cubic structures. So in any direction, they will have similar conductivity. So depends on the material structure. And this is the famous discovery of conducting polymers, again in the 70s. So these are all molecules you can see compared to, polyethylene, which is used in all these bottles and polythene sheets and so on. They are all basically carbon CH2, 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 CH2 connected with sigma bonds, no pi electrons. So if you take something like this, aniline or this example, this is called polyacetylene. So if you take ethylene, C2H4, CH2, CH2 double bonded, that is called C2H4. If you polymerize, you will get CH2, CH2, CH2. But if you take acetylene, you know what is acetylene? Carbon triple bond carbon. So 2 carbons connected with 3 bonds and 2 hydrogens. So if you open one bond, imagine like a gate, it opens and connect to another molecule. So you get a chain of carbons, but now you have double bond, single bond, double bond, single bond. So that is this structure. Now again, you have a lot of pi electrons. So if you create some, remove some electrons or add some electrons into this pi system, they become conducting. So this was a very important discovery. So this is what I told you earlier, this sort of rough chart of conductivities of various materials. Like quartz is one of the best insulators, very, very low conductivity. This is unit called Siemens per centimeter or ohm inverse centimeter. So 10 power minus 18, extremely small. But copper, platinum and so on are 10 power plus 6. And of course, conductivity is at temperature dependent. So I'm quoting them around 300 Kelvin, room temperature. So you can see there is, from copper to quartz, there is almost 24 orders of magnitude variation in the electrical conductivity. One of the very important, interesting properties that can change. You see, melting point of compounds. How much variation you will have? 50 degrees, 70 degrees, 100 degrees, 200 degrees, 300 degrees, that's all. But electrical conductivity goes from 10 power minus 18 to 10 power plus 6. Huge variation. Now, what is interesting about these conducting polymers, you can make these conducting polymers with variety of conductivities by changing the structure, by changing what is called the doping and so on. So that is the beauty of these materials. They are polymers, but electrically conducting, and you can play with their conductivity. And you can use it in, I'll come back to this mechanistic aspects after this. You can also create what are called electroluminescent materials. Again, something which is now day-to-day thing. You have what is called all these LED lights, not LCD, light emitting diodes. So these are based on a phenomenon called electroluminescence. Again, the mechanism I'll come to later. Basically, luminescence, light emission. You have fluorescence, phosphorescence, various kinds of luminescence, electroluminescence, chemiluminescence, bioluminescence. There are a lot of phenomena. Thermoluminescence, by heating, sometimes they emit light. So this luminescence, which is created by light absorption. For example, in old tube lights, I don't know, nowadays we don't see them anymore. You had these tube lights, you have seen? So they take, and then they come. They have to create an electric discharge inside. They are fluorescent lamps. That is the term that was used. That happens due to fluorescence. That means you actually basically excite some mercury atoms inside. They emit ultraviolet light. That falls on some phosphors, which absorb them and emit light in the visible ray. So this is photoluminescence phenomenon. But LEDs, you apply an electric field, it gets excited, the molecules or atoms and so on get excited, then they emit light. So that is why they are called light emitting diode. They have a diode structure. So you have a source and a drain and so on. So organic molecules like aluminum quinolinate and this is a polymer. So these were all shown to show electroluminescence properties. So they can, in fact, you have heard the term OLED? OLED TV? Many of these companies have, what is that O? Organic. They are called organic light emitting diodes. They are based on, they are commercially available now, using organic polymers which show light emitting property. They are used in display systems, sensors and so on and so forth. So the common electroluminescent materials, zinc sulfide, gallium arsenide and so on, many alloys, semiconductors and so on. But in 87, there was an important discovery. This is an organometallic compound, aluminum and quinolinate. And later on, there was a famous paper in 1990 where this is an organic polymer. It's a phenyl group and an ethylene group. It forms a polymer. Lot of things have to be hooked. There is a lot of synthesis and so on involved. But that also shows electroluminescence. So these are the sort of genesis of these OLEDs, organic light emitting diodes and so on. What about magnetism? Because I talked about conducting materials, luminescent materials, nonlinear optics. Magnetic materials is another important thing. And what are the classical well-known ferromagnets? When we say generally magnet, we mean ferromagnets or ferrimagnets. These are iron, cobalt, nickel, and some alloys of them. But then this molecule, this is a purely organic molecule again, nitrogen, carbon, oxygen, hydrogen, and so on. But you can see there is some spin on them. You have to have unpaired spins. So the interaction between the spin magnetic moments give rise to ferromagnetism, ferrimagnetism, antiferromagnetism, and so on, how they couple. So there was an organic compound made which shows ferromagnetism at a very, very low temperature. There is any magnet, even iron, is a ferromagnet, but above a certain temperature, it becomes non-magnetic. It becomes what is called paramagnetic. So that is called a Curie temperature. So below that, it will show ferromagnetic property. So any ferromagnet has some phase transition. And this, of course, has a very, very low phase transition. That means it is mostly paramagnetic. But if you cool it very, very low temperature, it will start showing ferromagnetic property. Ferromagnetism, in a very, very simple sense, is when all the spins get aligned within the material. The spins talk to each other and they become aligned. There is a lot of theories behind why they do that, but then they show magnetic properties. And there are ferroelectrics, nanocrystals. Actually, it's an endless list. So now that we went through all this, I'll just quickly now, I don't know where we are in time. You guys are getting tired? Because you sat through one more lecture earlier, which I did not sit through. So I'll have to be considerate about that, yeah. But anyway, by the way, if you want to interrupt me anytime, I forgot to tell you in the beginning, please do. Depending on the time, we can stop anywhere. This is a long story, it's an emerging, continuing story. So anyway, you got some rough idea about what are these materials. Now a little bit deeper into the ideas, I'll try to go through a little quickly how these materials, I just said you are assembling using some forces, but what is actually that you do in a lab? That is something I can roughly tell. And these conjugated polymers, conducting polymers, magnetic, depending on the time, and liquid crystals, I already promised how that LED works, that ideas and so on. And at the end, depending on the time, something called molecular devices. A molecule can act like a transistor or a diode and so on. So these are called molecular devices. So depending on the time, we'll go through. So this I'll run through a little quickly. Okay, it's a little descriptive. So assembling them, you can use various tricks: crystallization, nanoparticle colloid synthesis, various thin film assemblies. So this is just an example. There are hundreds of techniques. So crystallization is one of the most common. You have to make a solution. These are all well known to you. Cool it or evaporate it. You will get some. Simple example is if you take some sodium chloride at home, dissolve it in a glass of water, leave it for a few days, you will see beautiful crystals of sodium chloride forming at some point by the time this evaporation happens. Or on a cold night, if you use some hot water, dissolve it and keep it at cold, slowly they will crystallize. So sodium chloride or alums, and so a lot of things form very beautiful crystals by cooling. Then there are various other techniques, evaporation, something called a slow diffusion. For example, this is a very well-known method called a colloid method. You take a compound which is dissolved in an organic solvent, and the compound is insoluble in water. Many organic compounds are insoluble in water, but they dissolve in organic solvents like toluene or tetrahydrofuran or things like that. And then you inject them and then do some ultrasonication to make it very uniform. This process is called reprecipitation. You will see very, very fine. Colloid is basically something which sort of scatters light. So it's not transparent, it is more like translucent. And you can grow in our lab, just to give a beautiful picture, you can grow beautiful crystals like this of this. This you can see the size is extremely small. So these are sometimes called nanocrystals because their dimensions are in the order of a few nanometers. Very thin plates, and they have some interesting properties, optical properties and so on. So this is just one way of, and this is a method of imaging them called atomic force microscopy. I think during your program somewhere maybe you will be taken to some of the labs here where they have all these microscope facilities and so on. So you can image them, you can see, and they have some interesting properties. Or you can make very thin films using what is called spin coating. Because if you take a solution of something, let's say polymer, you dissolve it in some solvent, you put a drop, let it evaporate, you will get a polymer film. But it will be thick in the middle, it will be thin at the side, it will be sort of very non-uniform. But when you do want to do some detailed study, you want a very uniform film. So you do what is called spin coating. So you spin it at a very high speed, and depending on the spin speed, you can make them very uniform, thicker, thinner. You can play with all this. So these are techniques just to give a feel of how people make these films. Or you can do what is called physical vapor deposition. You can heat something which can be sublimed. You know what is a sublimation process? Phase diagram. You go from solid to the gas phase. What is a day-to-day example? Oh, okay, you have studied all this. Wonderful. Yeah. So that is why the cockroaches don't like it, right? Because that vapors are coming out of this. Yeah. And after some time, the naphthalene ball is gone. So you can, of course, that happens at room temperature, but many materials you need high temperature. So you can heat it using various methods, and that vapor will go and deposit. And you can use organic compounds, you can use inorganic material, various materials. You can then, using some microscopy, you can see how the particles are formed, and you can see whether they are oriented. Again, some examples from our own laboratory work. So I just picked. So using what is called X-ray diffraction technique, you can tell whether these crystals are oriented with some crystallographic axis along one direction or the other. If they are random, you will get all kinds of peaks. If they are very organized, you will get only certain specific peaks and so on. This is based on what is called Bragg's law. You have heard of Bragg's law, right? Bragg's law? Okay, you have not studied it. X-ray, very famous, like sodium chloride. How do we know sodium ion is here, chloride ion is there? Again, sodium ion is there. You have heard of sodium chloride structure? That crystal structure that is determined using X-ray diffraction. And the basic concept for that comes from what is called Bragg's law. So Bragg's law tells you, depending on the angle at which the X-ray falls on the crystal and the planes of atoms and so on, the angle between them, wavelength of the X-ray, and the distance between the planes determine this outcome, the scattering. So it's a very well-known law, and using that you can calculate what is the distance between the planes and things like that. So just to tell you, these are methods to make thin films. What else is there? Yeah, there is a very famous trick called a layer by layer assembly. That is, you take polymers which have charge on them. There are many polymers which are charged. What is the famous polymer in our body which has charges? DNA, yeah? Right. So DNA, for example, has some phosphate ions and so on. So you can make sodium salts of that or various salts. So these are polyanions. Similarly, you can make polycations. So if you take the solution and then dip a glass slide, for example, take it out, that polymer has coated here, then you wash it in water. Normally, all the material will go except one layer of the polymer. Because of that strong electrostatic forces with the glass surface, they will remain. Then you can put it in polyanion and then keep on doing. This is called a layer by layer assembly. You can do very controlled growth of layers of polymers. So many of these things have various properties depending on the molecule that you are actually absorbing there. There is another famous one which I should tell you, which I think you should hear about. This is called a Langmuir-Blodgett technique. This is a very, very famous technique which was developed by these two people, Langmuir and Blodgett. Actually, Blodgett was a technical staff in the lab. Her job was basically to clean the glassware, make solutions and so on. But then her name became very important because she also developed how to make these films. The idea is very interesting. There's a long history to it. But the interesting idea is this is one of the very early experiments where you could actually get the size of molecules. Because molecule size is in the angstrom units, right? Few angstroms. So a very simple experiment. How does that experiment work? You have a layer of water. This is just a schematic. This is actually the trough on which you can do this. You have some water in a Teflon trough. Then you have these molecules, which is just a schematic cartoon drawing. These are called amphiphiles. Best example is our soap. What is soap? The basic chemical part. It is a fatty acid, salt, basically, sodium salt or some salt. For example, fatty acids are with long carbon chains with carboxylic acid group at the end. And if you make a sodium salt of it, that sodium carboxylate group is water soluble. It is called a hydrophilic. and the carbon chain is hydrophobic. So these kinds of molecules, so this is the hydrophilic, these are called amphiphiles. Okay, so if you take these molecules like soap molecules or stearic acid, various amphiphiles, you put it on the water surface, just a cartoon drawing of it. So the head groups will, these are called head groups, which are water loving. So they stay in the water and the chains stick out. Then you this of course a magnified drawing, okay, molecules you cannot see, it is so small. But if I magnify it sufficiently, this is how it, and use something called a barrier. So this is the actual mechanical barrier, you can push it using a computer control. Then basically what happens is these molecules get compressed. Because the chains cannot go into the water, head groups will get stuck, so they start ordering. So you can continue this compression, then finally you will get nicely ordered molecules on the water surface. Then what do you do? Okay, you can follow this using what is called the surface tension measurement. Okay, it is called surface pressure here because the difference between surface tension of the water surface with and without the amphiphile. And when the areas of is very large, it is called a gas phase. This is exactly like, you have heard of Boyle's law? Boyle's law, pressure volume relation for gases. So that is in 3 dimension. Imagine that happening in 2 dimension. So instead of pressure and volume, you will have what is called surface pressure and surface area. So it's a 2-dimensional analog of Boyle's law. So when the molecules are far apart, you have practically no pressure because the molecules are not touching each other. When they come closer, you call it a liquid phase, the pressure starts rising. When they become highly ordered, they become really high. Now the beauty is that, of course, if you go on pressing it, there are very weak interactions, they will collapse. The film will become all distorted and defect. Now, if you imagine this extrapolated here, you actually get the molecular area. So this is one of the very early experiments where you could actually get the dimension of a molecule. You don't need X-ray diffraction and so on here. Because it's a very simple idea, you know the number of molecules you've distributed. If you know the concentration and volume that you're putting, you can actually calculate the number of molecules you have spread. And you know the total area here on the water surface. And that area divided by the number of molecules will give you the area of one molecule. So it nicely gives you the area of a molecule. And what Blodgett showed is that then once you order them, you can take some surface, a hydrophobic or a hydrophilic surface, you dip it through that, this is called a dipper, and when you take it out, one layer of molecules will transfer, and so on and so forth. You can make multi-layer structures. These are called Langmuir-Blodgett film. This is again a picture from our lab, some amphiphile molecule. You can actually, this is again using an AFM. You can see nicely, these are actually thin films. If you look at the thickness, it's only 2.5 nanometer or 25 angstrom. 25 angstrom is the height of the molecule, length of the molecule. The molecules are all arranged. It is like, if you imagine in a helicopter, there's a crowd of people, when politicians come, a lot of people will gather. No, from the helicopter when they see, they will only see a thin film-like thing. So, but the thickness of that film will be the height of the persons. So it's exactly like that. Now, if you add a DNA, we did this experiment, because then the thickness goes to 5.5. The difference is due to the diameter of the DNA. So you can get very fine molecular information. These are all molecular materials because they are all made of molecules. They have some properties and so on, which I'm not going into. I mentioned already this, various donor molecules, just some examples. I'll run through this quickly because we are closing in on time. So these are all good organic donor molecules, acceptor molecules. I mentioned this TCNQ earlier. There are various things with cyano groups and so on. Now, what is the use of this? Now, if you take this molecule, you can lose an electron very easily. As I said, they are very easy to ionize. And this you can easily add electron. Now, when you combine the two, you have what is called a partial ionicity. This is very important because this is sort of schematic of what I told you earlier, like dosas packed, you have molecules packed. Now, if you have what is called the oxidation and reduction potential, that means the energy required to oxidize a molecule, remove an electron, and the energy required to add a molecule. If you balance it properly, then on an average, if these molecules are all oxidized and these are all reduced, then to jump one electron, or if all the molecules are oxidized, all of them have one unpaired electron, to jump one electron to here, it needs an activation energy. That means it is like a semiconductor. You need some energy to activate. Semiconductors have filled bands and empty bands. You need some light energy or heat energy to create free electrons to conduct. However, if you make partially ionic, that means only alternate molecules have a charge. The idea is very simple. If I have 10 donor molecules, 10 acceptor molecules. So only 5 electrons get transferred because of the energy required for removing electron and adding electron. So out of 10, 5 have charge. Out of this 10, 5 have negative charge, 5 had positive charge. So there are molecules which are not ionized, molecules which are ionized. Now you can jump the electron very easily, because if you have a cation and a neutral, if electron jumps from the neutral to the cation, you have cation and neutral. So there is very low activation barrier. They give rise to metallic conductivity. So this is how we understand how they become conducting. And as I said earlier, they conduct well along this axis, but not in this axis. So they are anisotropic conductors. And these are examples of superconductors. I will not go again into the theory. There's a lot of details about phase transitions and so on, but they show this TC is called the critical temperature, below which they show superconductivity. That means zero resistance in them. And this discovery of conducting polymers, as I said, it was known for a long time, what was called aniline blue and so on. But in the 70s, there was a chance discovery with this molecule called acetylene, I mentioned briefly. If you polymerize using certain catalysts, you will get some film. This was a very chance discovery. This is a very famous story. This acetylene is a gas, as you know. You know, in oxyacetylene flames, they have the cylinders, oxygen and acetylene. So when you combust them, you get very high energy. So you can fuse metals and so on. So this Japanese group, they had acetylene cylinders. So somewhere it got exposed to some aluminum and some metallic surfaces which can catalyze the polymerization, and they got this copper colored and some, depending on the conditions, some silver colored films, which are solid films, from the gas to the solid film. So this was a chance discovery. When they analyzed it, they found they were basically polyacetylene. So these are two different isomers of this, completely trans or completely cis. And the electrical conductivity of these are not very good. They are very, very low, as you can see, compared to copper. I showed you this chart earlier. Copper is 10 power 6 approximately. Teflon is 10 power minus 15. So these are somewhere in between, but not great conductivity, not like any metal. But the trick was, if you can add an electron or remove an electron. How do you add electron? Again, simple, expose it to some alkali metal, potassium vapor, sodium vapor, they will give an electron. Then there is something called band structures and so on, which we will not go into detail, or remove electron using bromine or some halogen. So now what happens is you are creating some charge here, or a negative or a positive. Now these can run along the carbon chain very easily. You apply an electric potential, this charge can move. Movement of charge is electrical conduction. Then the conductivity changes. From here 10 power minus 5, it goes to plus 10 to the power plus 4. Almost 9 orders of magnitude. So this is an amazing thing. That means you have a polymer now which is conducting. So this is what is called conducting polymer. This polyacetylene is not very air stable, but people develop many other polymers. You tell me when we should close. Is it getting late? Maybe another 10 minutes I will try to run through. Yeah. Okay. So these are the three famous names. In fact, they got the Nobel Prize in 2000 for this discovery. So there are a lot of Nobel Prizes, which I did not mention all of them along the way. But these guys, so he was a physicist, he's an electrochemist, he's basically a polymer chemist. So this is Shirakawa and McDiarmid and Heeger. So he sort of explained the theory behind it. So it's again a collaboration between physics, electrochemistry, organic chemistry, and so on. So, and there is a lot of polymers. Polyaniline is one of the very stable one, very easy to make. I don't know if I have a picture. And depending on the extent of oxidation, you can have colorless polymer. And if you oxidize it a little bit, you will get a blue polymer. If you make a salt of it, it will form green. And this is sort of electrically conducting because you have a charge which can delocalize. If you over oxidize it, again, it becomes insulator. So you see beauty of that. It's a polymer. Same thing, you just vary the oxidation. How do you do that? You can do it chemically or electrochemically. Electrochemically means you apply voltage. You change the voltage. You are applying higher and higher potential to oxidize it or reduce it. You can change the color of the film, electrical property, and so on and so forth. So these kinds of things find extent of oxidation. They find application in a lot of things. In fact, conducting polymers are used in various, one of the famous examples is sensors, for example. You know, with these diabetics, you need to measure glucose levels and so on. So a lot of sensors are based on conducting polymers. I may have some picture to show that later on in the devices. So organic radical, I think we are running short of time, so I'll run through very quickly. These are organic radicals which are very stable. You can make magnetic interactions between them. Just this one example will show you what is the power of this. So this is a simple organic molecule. This is called a Verdacyl radical. It has some unpaired electron which can delocalize, and you see this simple molecule. These two are very similar, except that here you put a phenyl group. So this is organic chemistry. You can add methyl group, ethyl group, phenyl group, a lot of things organic chemists do. Now you see the magnetic property. This is chi is called the magnetic susceptibility. So usually the susceptibility versus temperature, if you plot as a function of temperature, if it dips at a low temperature, the susceptibility is going down. That interaction is called antiferromagnetic coupling. That means spins like to align anti-parallel. But if it goes up, that is called ferromagnetic coupling. So spins like to align. Now just changing the phenyl groups, actually what happens is the spin density distribution, the spins are distributed along that. That how the two molecules next to each other overlap determines the spin interaction. By putting a phenyl group, you are actually creating a little steric problem. So the molecules move a little apart. The spin interactions are affected. So this is all spin physics controlled by organic chemistry. So this is where the molecular materials come in. So a lot of chemistry involved, a lot of physics to understand what goes on. And of course in applications in sensors and things like that. So this is, I already told you. Even fullerene, there is a famous example where you can create this Curie temperature below 16 Kelvin. This is a good electron donor. Fullerenes are good electron acceptors. You can charge transfer, create magnets out of them. Optical material, I think I'll run through. So these are fluorescent dyes, but usually dyes become non-fluorescent in the solid state because of what is called quenching process. But you can define, again, some example from our lab. There are many labs that have created this. You can create some molecules which are highly fluorescent in the solid state. Again, a lot of molecular structures and interactions between molecules in the crystals. You can use it for imaging. For these are stomata. You might have heard of stomata, right, in botany. So you can image them by putting these kinds of organic molecules. They are bright green fluorescence. So you can use it to image molecules or bacteria. So these are some examples from our lab, but there are many, many people who have done these kinds of things. You can, spores of bacterial spores, you can image them using these organic molecules. So these are all molecular systems which are used for optical application. Again, this example where you can tune them. I'll run through these. Are some examples of various exotic organic fluorescent materials. Let me not, I think we are running short of time. You can use lasers to write images. Again, using fluorescence, you can read them. I'm skipping it because of our shortage of time. So liquid crystals is important. So I'll just come back to that in another 2-3 slides. I'll try to close. So as I showed you earlier, is another cartoon drawing. If you remember, I showed you cholesteric phase, where you have molecules which are rod shaped, aligned in one direction. The next layer, they have slightly tilted. So they have formed a helix. So for a helix, there is something called a pitch. That means after how much distance, they come back 360 degrees in phase. So this N is called the director axis. So this axis is sort of forming a helical thing. This is very important. These are called chiral nematic. Chiral because they have a helicity. Helixes are chiral. They have sort of a right-handed and left-handed. They are not superimposable. Now, so the idea of this LCD, liquid crystal display units, the basic principle is all I'm trying to show you. It's based on what is called twisted nematic effect. Now, what is that? So here, these rods, this is just a schematic I made just to show you the idea. So this is the molecules of the liquid crystal. As I said, there is a helical orientation. Now, you trap them between two plates. This E1 and E2 are electrodes. These are called transparent electrodes because these are glass electrodes with a coating, usually of some indium tin oxide and things like that, which are electrically conducting, but transparent. It's important. It has to be transparent and electrical. So now you sandwich these liquid crystal molecules with a certain, actually this quarter of a pitch between two electrodes. In reality, it is like a plate. You put some liquid crystal molecule and you actually rub them and so on to orient them. Then you put another plate, electrode. Now, so that is the electrical part, and you can apply a potential across them using a battery or some electrical source. Now, there is another important component here. It's a polarizer, P1 and P2. These are polarizers. You have heard of polarizers? Polarizers are basically, when light travels, when a light is traveling in this direction, the electric field oscillates in the perpendicular direction and magnetic field in the opposite. So these electric field vectors are in all 360 degrees, normally unpolarized light. When you send it through a polarizer, only one component goes through. We call it a linearly polarized light. That means that if I have ordinary light, which is unpolarized, the electric vectors is oscillating in all directions with the frequency of the light. And when it passes through a polarizer, only one component remains. That is vertically polarized. Now, if I rotate the polarizer, I will get a horizontally polarized. So this P1 and P2, P1 is a vertical polarizer, P2 is a horizontal, what is sometimes called a cross polarizer. Now, this is the setup. Now, imagine light coming. So light is coming through. So it is vertically polarized. It meets this or a liquid crystal, and the light travels through them. As the light travels, it's a plain polarized light. Because of the helicity of the liquid crystal, this light actually rotates. And by the time it reaches this electrode, the light is in this direction and it nicely goes through the cross polarizer. So you see light. That is called the off state. I'll tell you why. Now imagine, just now please remember this. Now I'm going to switch it on. Just another next slide. So when I switch it on, this electric field is going to be applied across that liquid crystal thin film. Now this is what happens. When the electric field is applied, because they have some polarity, these molecules, they all get aligned. Because they are very weakly interacting, I told you, so very, very weak, a few volts is sufficient. They get aligned. Now look at the fate of light. The same light which was polarized has come through. Now because all the molecules are aligned now, there is no helix anymore. So light travels with the same polarization. Once it comes here, it finds a cross polarizer. It cannot go out. So it becomes dark. So that is called the on state. Now why do I call this the on state? If you see LCD, maybe I have a picture. Where I see the 8, those are little liquid crystal cells. The dark one is what we call on, because that is what tells us there is some signal, some image. You remove one of them, it will become 6, and if you remove the other one, it will become 9, and so on. So you can create all the kinds of patterns. So wherever the light does not come through, so there are a lot of liquid crystal pixels are there, and depending on where you apply the electric field, it will become dark or light. There is something called a backlighting. So the blue light is the backlighting. So wherever it becomes dark, it gives you some information, some display or whatever. So this is how you create images, and you can make all kinds of beautiful pictures, rose flower, whatever you want, depending on how you arrange these liquid crystal units. So this is the beauty of these molecular systems, because if it was a perfect crystal, no electric field, you may need kilovolts and so on, then it will burn up. Here you need a few volts, even a simple battery. For LCD displays, you use few volts. You can create these images. So this is just as a nice example of how it becomes commercially very relevant, because that weak interaction between the forces is critical here, because of which magnetic field can be used, electric field, optical field, various things can be used. Yeah, I think I'll skip this. So the various application sensors, you can do humidity sensing. I think we have really run out of time. I don't want to trouble you. So this is something from different labs. This electrochromic devices is again very important. I'll just give you an example. What are called smart windows. In many aeroplanes now, the aircrafts, the windows, by just applying a voltage, they become dark. And this is using what is called electrochromism. When you apply electric field, those polymers I showed you, I'll tell you quickly the principle. I told you polyaniline. You apply different voltage, the color changes. So in principle, you can do with the various kinds of conducting polymers. You apply voltage, the color changes, so you become dark or blue or red and green and so on. So this is some example of using a 3 volt. This becomes transparent, or you apply minus 3 volt, they become dark. So these are called smart windows. So these are all based on this conducting polymers, and there are various other examples of electrochromic materials. Electroluminescence, this is the principle which I mentioned earlier. So electroluminescence means basically you want to create an electronically excited state. Usually photoluminescence, you apply light, UV light, you create the excited state, it emits in the visible range. There's something called a Stokes shift. But in electroluminescence, the principle is you apply an electric field. If you apply an electric field on this, these terms you might not have heard of, these are called molecular orbitals. That means where the electrons are present, no electrons. Highest or occupied molecular orbital and lowest unoccupied molecular orbital. Depends on the molecular structure, you have various energy levels, right? So when you apply a cathode, you can put an electron on that, and using an anode, you can pull an electron or add a hole. Hole is like removing an electron. And now you create basically an electronically excited state. When it comes down, it emits light. So this is the principle. So instead of using light to excite an electronic state, you use electric field, create an excited state. When it comes back to the ground state, the electron jumps back, it emits light. So that is how all these LEDs work. They use semiconductors or these conducting polymers and so on. So this is some example, the electrochrome displays. Okay, this is again some mechanical actuation. I think just to show you a picture. Okay, I don't know if you can do various things with these molecular crystals. If this movie works, there's some sort of a crystal under electron beam. You can make them move. So these are called actuators. So again, organic molecules using electric field, you can play with them. So you can model them and so on and so forth. I'll skip all this. This is the last example. This is a very famous example in what is called supramolecular chemistry. There's something called mechanical bonding. We have heard about covalent bonds, where electrons are shared. Coordinate bond, there is a partial polarity on them. Electrostatic bond, you have charges. You have so-called metallic bonds, where you have metal atoms with free electrons floating around, holding them together. Something called a mechanical bond. That means you have these molecules are sort of formed knots like this, so you cannot take them apart. So it's again a bonding. It is like making two knots and holding them together. So there's a lot of interesting things. There was some Nobel Prize given and all that. And using various pH changes, you can make these mechanical things move. This is called a mechanical shuttle. These are called molecular machines. It is like exactly like a machine moving part. You can make molecules move using pH or temperature and so on and so forth. So I think I'll close it here. Sorry, I had to rush through a little bit towards the end because it's a long story. But the whole idea is not that you learn all the things in one shot, but you get sort of sensitized with these ideas. So many things are happening around, and things where you find it fanciful, you should pursue that. That is the whole idea of science, right? We ask questions. So many things that I gave you so that you can think about questions on them. So this sort of thing. This is a textbook on, I'm supposed to put this at the end of my lecture, textbook on materials which I have written, because the publisher insists I should put it at the end of my talk, so I just kept it. Sorry, I've used most of the time, but a few questions, if there is time, we can take. Yeah, no discussion, or anybody wants to ask anything, or we don't have time?
Thank you, Radhakrishnan sir. Your enthusiasm and wide range of knowledge on molecular materials has inspired us. You have shown us such materials have changed the history of humanity forever. Speaking of history, we loved the bits of history you added to this lecture. From organic LEDs to liquid crystal displays to electrochromism and uses of SHG in nonlinear optics, you have made us appreciate the uses of all molecular materials. Thank you, sir.